Hey team, remember we talked about this unit, our big question being how can the change in a single nucleotide bring about a genetic disease? That's what we're looking at here with sickle cell disease. Normally, your body produces adult hemoglobin gene, which is what carries oxygen in your bloodstream. And so you get normal hemoglobin and you carry your red blood cells in normal shape and carrying oxygen just right. But with a single change in a nucleotide base pair, we end up with sickle cell hemoglobin, and that isn't good. These things, not the right shape, they don't bounce through the bloodstream properly, they hook onto each other, they gum up the works, and you end up with poor oxygen delivery, you end up with pain that we talked about with Omar. But there's this other thing called fetal hemoglobin. And you know what? It's a slightly different form. There's gamma here. But guess what it produces? Totally normal red blood cells. Huh. But once you're born, there's another gene that is expressed, and that makes a protein called the BCL11A. And guess what that does? That shuts down the production of normal red blood cells, and we're back to just making sickle cells. Huh. Bummer. So, as a little primer, backing up a minute, in your blood vessels, you've got these erythrocytes, these red blood cells, and their sole job, they're not complicated. They got like a one-trick pony, carry oxygen. You know that if you put a piece of metal, like you put a nail outside, come back later, it will rust because it is made of iron. And iron connects nicely with oxygen. We know it out in the regular world as rust, but it is that affinity, that connection between oxygen and iron that allows your red blood cells to carry oxygen through your blood. That's working in a perfect world. So why, if we have this totally functional, normal hemoglobin when we're in utero, do we stop making it? To answer that, let's just back up a hot minute here, all right? When you are not yet born, when a baby's not yet born, what does the mom's body do for that baby in utero, still in the uterus, in the womb? Everything. The mom is breathing for that baby, the mom is feeding that baby, and the mom is taking care of wastes for that baby. Right now, this little kid, lungs are not yet working, will not be working until it takes its first breath. Likewise, its kidneys. You know, you're not peeing in utero. What's happening there is that the mom's blood is taking any waste back out through her blood to be filtered out by her kidneys. Oxygen comes in through that umbilical cord and gets delivered to the baby. But wait a minute. Does the mom want to give up that hard-earned oxygen to the baby? Not really. So that's what's going on here. When we're adults, we have the two alpha hemoglobins and these two betas as well. This is the normal adult hemoglobin. It holds oxygen, it gives up that oxygen. It holds oxygen, it gives up that oxygen. This is what mom's got going on right now. So baby needs to up the game. Does that with this fetal hemoglobin that's instead of got these betas, has got these gammas. Don't worry about what's really going on here at the atomic level, but what it is it turns out this holds oxygen better. This is that little greedy little kid saying, gimme, 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 give me that oxygen. And that is how the baby basically can get oxygen from its mom's blood. But once you're born, we don't need that anymore, all right? We don't need that anymore. Remember Omar, our man? When he was in utero, he made all these perfect, beautiful little red blood cells, carried oxygen just fine with the fetal hemoglobin. But when he was born, he had that one nucleotide change and started producing these sickle red blood cells. Right? The reason up till about age 2, it takes about 2 years to fully transition from fetal hemoglobin to adult hemoglobin. As an adult, you don't want your red blood cells holding on to that oxygen a little bit more. You're not trying to hold on to it from anybody else, right? Like if I breathe in, I want my cells to be able to grab that oxygen too when they need it. So I can't have the red blood cells using that fetal version to hold on to it a little. It just makes it a little bit harder for the body. Omar, though, if he could go back to this, is got to be way better than having sickle cells. So how do we treat Omar? How do we treat Victoria Gray using CRISPR-Cas9? All right? How do we make that happen? So what we need to do is, remember, we got the shutdown. This protein, the BCLL11A, is locked onto the DNA. It says, don't read the instructions on how to make fetal hemoglobin anymore, so that's shut down. Bummer. Not working. I don't have those. So what we need to do then is get rid of that fetal hemoglobin. That takes the brakes off, and we now have normal red blood cells again. How's that work? Again, using CRISPR-Cas9, we have these little segments of DNA where we can put in a primer and say, hey, it's like Control F. Go find this. Gets in there, cuts it out. We cut out the BCLL11. We're not fixing the error in the adult hemoglobin that leads to sickle cell. I imagine they're still working really hard at that piece because it seems to me the easier fix, but this is the fix that it turns out for now is easier, that we use that CRISPR-Cas9, Control F. Hey, would you go find this gene in the genome and cut it out? And that's going to take care of this protein. And without this protein, guess what? Victoria Gray, Omar could be making totally normal red blood cells. They're the fetal ones, which hold a little closer to that oxygen, but better than the sickle cell version. Yeah? So that is your primer on what's going on with sickle cell disease, what fetal hemoglobin is, and how we can use CRISPR-Cas9 to try to fix that.